Network troubleshooting using Wireshark.
Today, we're going to cover how to troubleshoot some common failures with the TLS protocol using Wireshark. TLS, also known as Transport Layer Security, formerly known as SSL, is a protocol widely used to secure and authenticate connections on the public internet. Not only that, many large enterprises are also using TLS to secure data between systems within their own data centers. When a TLS connection can't be established, generally speaking, it's the handshake which fails. So it's important to understand the steps in the handshake if you're going to use Wireshark to troubleshoot it. So to get started troubleshooting, the first thing I want to run through is what a good TLS handshake looks like in Wireshark. With any sort of packet analysis in Wireshark, if you really want to get good at it, it's important that you spend time looking at good captures or captures of good data. This way you actually start recognizing some of the patterns, and at the same time you can actually pick out a lot faster when the pattern doesn't hold and there may be a failure. And you'll see what I mean in a sec. Before we get into Wireshark though, I want to point out two resources that I will link in the description. The first is this nice guide, the illustrated TLS connection. This is at tls.ulfheim.net. And what this is a message by message breakdown of a TLS 1.2 handshake. For the purpose of this video, we're going to be sticking with TLS 1.2 and below, only because it is more widely used than any other version of TLS. TLS 1.3, while it is available and being used by many systems on the internet, it isn't as widely used as TLS 1.2 yet. In future dates, I may do a video on 1.3, but for now, let's stick to the TLS 1.2 handshake. So I would highly recommend that you spend some time going through this. This document will actually detail every message along with what information is passed from the client to the server or from the server to the client. And you can actually use this and follow along packet capture to actually look at these messages in Wireshark. The second document I'll reference is the actual RFC for TLS 1.2. It's a little bit more advanced if you're not really a network geek like I am, but if you are or just curious about how these protocols are constructed and designed, this is a really good document that goes through it literally message by message and gives you a full explanation on how it works. So without further ado, let's open up Wireshark. And I'm also going to open up a Linux virtual machine, which we're going to use to generate some of this data. So in these examples, I'm going to be using the curl command in Linux to run several different tests to a public website. And we're going to look at a successful handshake, and we're also going to look at a few problem scenarios as well. So the website in question that I'm going to use as a tester for my first successful test is magicball.net. This is a fan site for the 90s video game Twinson's Odyssey. You may want to look it up. So the IP address here is 213.167.243.131. So I'm going to apply that as a host filter in Wireshark so I can just filter out all the other noise and just get data going to this IP and from this IP. So host 213.167.243.131. Okay, and the second thing is I'm going to specify my data interface, which in this case is my wireless. There goes my filter. Host is 213. There it is. This is my history. Okay, so let's get started there. You shouldn't see any data now until I do my first successful curl. And what I'm going to do, curl https www.magicball.net. All right, so just by looking at the curl output, I can see that I see quite a lot of the hypertext of the web page itself. You can see here there's some CSS and some actual text and links. Usually when you are looking for a successful connection over TLS, you're looking for a connection which gets to the point where it's exchanging application layer data. TLS is used for multiple different apps. Usually people think of it only as HTTPS, which is HTTP secured with TLS, but TLS can actually be used for things like FTP, could be used for things like LDAP, etc. But usually when you're talking about troubleshooting TLS and troubleshooting handshakes, once a handshake is successful, that's when the client and the server can actually start exchanging application layer data, meaning in the case of HTTPS, that would be HTTP data. So in this case, I see actual HTTP data, and I'm going to assume that the handshake was successful, but I can also show you that from Wireshark. So I've got a whole lot of packets that showed up as soon as I did that curl, so let's go through it from top to bottom. So the first prerequisite of a TLS handshake in Wireshark, or TLS handshake in general, is that a TCP socket must be open. So a TCP connection is established with a three-way handshake. We see here a SYN, or synchronized packet, coming from my virtual machine, a SYN-ACK coming back from the web server, and then the ACK. So at this point, I've got a socket open to TCP 443 on this server. Now, the fourth packet in any TLS connection is the client hello. Now, the client hello is a packet that must come from the client. And what it is essentially a proposal. It's a proposal for various parameters that the client can support in creating this secure connection to the web server in question. So in this case, if I actually open up that packet in Wireshark, the Wireshark dissection will show me a whole bunch of information that is included in this client hello, or included in this proposal. There are things like the TLS version. You've got some random data, which is used for key generation, a session ID. You've also got a list of Cipher suites, which is going to come up later. Now, Cipher suites are essentially different protocols which define the encryption which will be used in the eventual connection, as well as the authentication methods which will be used in the connection as well. When I send the server a list of Cipher suites, and also when I send the server the version I support, what I'm saying is, here is what I can support. I can support up to TLS 1.2, and I can support all of these 31 Cipher suites. So that proposal goes over to the server for the server to look at it and say, okay, well, I can do TLS 1.2, that's good, and I want to use this Cipher suite or this Cipher suite, etc. There's lots of other information included in the client hello, as well as lots of extensions, which are really interesting, but we're going to skip them for today. So the client hello is sent out. It's acknowledged by the remote web server. And this is really important. You've got here an acknowledgement that has no data in it. So we consider this a naked ACK. A naked ACK is really just the TCP layer saying, I got this packet back to the sender. It's not saying that whatever is in this client hello is acceptable, right? So the remote web server is not saying, okay, I like your parameters that you're sending me in the client hello, this is good. An acknowledgement is really just acting at layer 4 in the OSI model, which is the transport. And it's saying, in TCP speak, it's saying, I'm acknowledging that I got this, now let me process it and I'll get back to you. And we're going to see that come up several times in this example, as well as the problem cases. So in response to that client hello, if the server is okay with the proposal in the client hello, the server will send its server hello. And there's many similar fields in the server hello to the client hello. So we have another version, which means that I've settled on version 1.2, so that's good. And you can see here with Cipher suite, we don't have a list, but we have a specific Cipher suite that was chosen. This Cipher suite was actually chosen out of the list which the client sent over. So if I actually pull this up, C02F is right here. And that's going to come up again in one of our problem scenarios after this. So the server hello comes in. It'll say we're going to do TLS 1.2. We're going to use this Cipher suite to do it. We've got some extensions, which we can look at later. And again, we see the response to that is just a naked ACK. So the client's saying, okay, yeah, you sent the server hello. I got it. I'm going to acknowledge that I received it. The second thing the server is going to send is its certificate. Now, TLS is used not just to encrypt and secure a data stream between two hosts, right? It's actually used for authentication as well. So what this means is that when I'm trying to connect to a remote web server, say google.ca, I want to make sure that that web server is actually Google, as opposed to some other third party who's masquerading as Google. I want to make sure that that server belongs to Google. And that is accomplished using public key cryptography and certificates. So a certificate is attached to a specific web server that you're connecting to. And when you're trying to establish a TLS connection, the server needs to send you that certificate. And the client has to look at the certificate, analyze it, and say, do I trust that this is google.com, or in this case, magicball.net? Or do I not trust it, in which case I don't want this communication to go forward. Wireshark, when you actually look at the certificate packet, actually breaks down the certificate into all of its individual fields. So you can see here, for example, the common name of the cert, in this case the magicball.net. You can see here things like the algorithm used for the encryption. You can see here the issuer of the cert is listed, the validity of the cert is listed, etc. You can also see that the server sent not only the certificate for magicball.net, but it sent its intermediate certificate as well, in which case this is Let's Encrypt, which is a free certificate authority. So the responsibility of the server is to send the cert, and in this case the intermediate or root cert. The responsibility of the client is to analyze that and say, hey, do I trust it? Is it valid? Is the certificate authority legit, or is it some kind of random CA that I don't know? And if it likes all that information, then it'll accept the cert and we can move on. So you can see here in packet 9, we've got another naked ACK. So the client's saying, I got your cert. The server then sends two more messages, server key exchange and server hello done. In this case, it combined both of those messages into the same packet, which is why it's in the same line here. And Wireshark lists both messages with a comma. We get another naked ACK. At that point, the client's turn is up, and the client has to send the client key exchange, client change cipher spec, and an encrypted handshake message. Finally, the server will do another response to that. It'll send its own change cipher spec and encrypted handshake message. And at that point, the actual application data can flow back and forth, which you can actually see here because Wireshark will flag it as application data. Now, this last stage where you see change cipher spec is really important. The change cipher spec messages are really the end of that handshake. And usually when I'm analyzing a PCAP with TLS and looking for handshake problems, whenever I see each side, the client and the server, send the change cipher spec message to the other side, that's generally when we can say, okay, the handshake is finished. Now we can start exchanging application data. It's all going to be secured and we're good to go. So I usually use that as a method of detecting that the handshake is done. And sure enough, you can actually see after that point, we see lots of full-size packets being sent and acknowledged back and forth. And this is going to be that HTTP data which we saw within the curl. So from top to bottom, we've got, again, the three-way handshake, a client hello, a server hello, server certificate, server key exchange, server hello done, client key exchange, change cipher spec, and then a change cipher spec from the server. If I go back to that web page quickly, you'll see that a lot of the names here match up to the names we just went over in Wireshark. So you can spend some time going through this to look at the definitions of precisely what's in each of these messages, besides the few things that I pointed out. All right, now that we've covered what a successful TLS handshake looks like, we're going to jump into some problem scenarios that you may encounter when you're trying to establish a TLS connection and it's failing. So the first one we're going to look at is what happens when you're trying to establish a TLS connection on a port or TCP port that's not actually running TLS. Now, TLS is not specific to a port. A lot of times when you mention TLS, people think TCP 443. TCP 443 is generally the standard port used when you're making a HTTPS connection, which is HTTP secured with TLS. It doesn't necessarily have to be that port though. Like I mentioned earlier, TLS can be used for securing FTP connections, LDAP connections. Really any TCP protocol can, in theory, be secured with TLS. One of the prerequisites of that though is that the server in question that you're connecting to actually has TLS enabled on the port you're connecting to. So in this case, what I'm going to do is a curl to the same website, magicball.net, and it's HTTPS, so I'm specifying that I want to do a secure connection, but I'm telling it to use port 80. Now, generally in HTTP, port 80 is reserved for plain text connections for HTTP. So let's see what happens when I say to that web server, hey, let's do a secure connection on your plain text port. All right, so we get this generic error from curl, SSL routines, SSL3, get record, wrong version number. So who knows what that means? That may be an error message that shows up in a server log or an application log of yours, and you're not necessarily sure what it means. So you take a packet capture and you look at it. So Wireshark shows a stream of data that doesn't actually look like a TLS handshake at first glance. You see the sync and ACK, so the actual TCP socket is created. That's a good step. But then after that, it doesn't look like you see like the client hello, for example, or any other TLS message. You get this HTTP response back from the server that says 400 bad requests, and then you see the connection fin. So clearly the connection doesn't go anywhere. You don't see a whole lot of data through the connection, and it's closed pretty quickly, but it's good to understand why. So one of the tricks that I want to show you is that I know from this example that I'm trying to connect to this port on TLS. Wireshark, by default, when it's trying to do the dissection of the data, won't know that you want to look at what TLS looks like on port 80. It sees that you're connecting to port 80 and it assumes, okay, this is port 80, it's plain text HTTP. So that's how it's dissecting or interpreting the data and showing you what the output looks like. In this case, it shows you, for example, we've got an HTTP bad request here. So in order to actually dissect this as TLS, what I've got to do is actually go over to the TCP layer here. So you can either select any of the packets, go down to the TCP layer, right click, and then click decode as. And then from here, you've got to select the value, which in this case, select the destination port, which is the application port. In this case, it's 80. And then under current, you want to change this down to TLS. Go to OK. And right away, you see that this fourth packet here actually turned into a client hello. Now, this didn't actually change any of the contents of the packet. What it did is Wireshark is just interpreting it using a different filter. So in this case, it's interpreting it as if this was a TLS packet, and it's actually showing you and dissecting all the TLS fields for you, whereas it wasn't doing that before. Now you can see here we've got the sync and ACK. The client hello goes out. That's the same client hello we saw before in TLS 1.2. We've got 31 different suites. We see that the remote server sends a naked ACK. So again, this doesn't mean that it likes the client hello. It just means that it received the client hello. And then immediately what we see is a response to it with an HTTP 400 bad request. Meaning, I don't know what the request is you're sending me, and I'm going to tell you it's bad, and then I'm going to close the connection, which is what happens here with the fin, and then we reply with a reset. So the way you can interpret this is that in any TLS speaker, it has to understand at the very least the client hello and respond to it in some way. Either it responds to it negatively and because it doesn't like something in the client hello, which we'll cover next, or it just doesn't understand it because it's not speaking the TLS protocol. And that's the case here. You can see this service port TCP80 is actually expecting just a plain text HTTP protocol. So when we connect to it using TLS and send a client hello, it doesn't know how to interpret it and then sends HTTP 400 bad request. So if you ever see something like this in a packet capture, what you can do is check on the server side to make sure that the port that you're actually trying to connect to has TLS enabled. For HTTP, it's a little bit simpler because you've got 80 and 443. It's pretty standard. One is plain text and one's not. But you might be trying to enable TLS on, say, a port for Microsoft Exchange or for LDAP. And in those cases, you may think that you have TLS enabled, but then you look at a packet capture and you say, hey, my client's sending a client hello, but the server's coming back with something like this. Let me check the configuration to make sure that TLS is actually enabled. All right, so the second scenario we're going to cover is what happens when the port in question you're connecting to is speaking TLS, but there's something that the server doesn't like about the client hello that you're sending. Either it doesn't like the Cipher suites that you're offering to actually encrypt and authenticate the connection, or it doesn't like the version you're sending. So to simulate that, again, we've got the capture refreshed. We're going to do a similar curl. I'm just going to clear off this console. To magicball.net, in this case I'm taking out the port 80. But what I want to do is specify a cipher list. So for the ciphers, I'm going to specify triple des. This isn't just going to use one cipher. There's actually a list of ciphers associated here. But for the sake of this illustration, I just want to show you what happens when you have a limited cipher list. So let's hit go. Now again, you've got curl error saying that the handshake has failed, which is good that it tells you the handshake failed, but it doesn't actually tell you why it failed. And this is where Wireshark is useful. So looking at the actual packet capture, we see we have our three-way handshake, send, synac, ack, that's all good. Client hello is good. Naked ack coming back saying, hey, the web server got the client hello, which we'd expect. But then immediately after that packet, we see an alert that's saying alert level fatal description handshake failure. So clearly this is what curl was picking up. There is a handshake failure. The handshake doesn't get to the end, which is the two change cipher specs. So we got to figure out what's going on. So if I open up this client hello packet, and I actually go through it, I can see here the version is 1.2, but the cipher suites, there's only 4 suites. If you remember from the previous examples, there was something like 31 different suites we were offering. Not only that, these suites that are being offered are pretty legacy. I don't know of any modern web servers that run any of these suites, especially the empty renegotiation one. Now, as we mentioned when we looked at the healthy handshake, the server that you're connecting to has to support the version you're connecting on, as well as it has to support at least one of the cipher suites that you're sending. And in this case, the remote server doesn't support any of these cipher suites. And what happens is immediately after the client hello, you get the alert from the server and then the connection is closed. Now, if you ever want to validate this, I'm going to post a link in the description to SSL Labs. SSL Labs is a site that you can use to actually assess the TLS parameters of a website on the internet. So SSL Labs allows you to plug in, say, magicball.net, and it'll spit out all the versions of SSL, or TLS, I should say, that it supports, as well as the cipher suites it supports, and a lot of other information about TLS on that server. But for this example, you can see I've got 3 legacy cipher suites. Clearly, the other side doesn't like these and needs something that's a little bit more modern. And then it alerts and closes the connection. So if you run into this scenario, what I would say is you need to check on the client side to make sure that the client is configured to send multiple cipher suites. The more the better, because that may you have more chances of the server accepting it. But also keeping the certificates, or sorry, the cipher suites update, because over time, certain cipher suites are introduced to the TLS protocol, and other cipher suites are removed for security purposes. So it's always important to maintain either the actual specific configuration in your app for SSL on the client side, or just to keep your SSL libraries updated if you're doing some kind of custom application. So for our third failure scenario, we're going to look at what happens when, as an SSL or TLS client, you're connecting to the server and the certificate presented back to you is not trusted by the client. So in this case, what I'm going to use is a different website. It's a website, badssl.com. This website is also a good resource if you're trying to learn about SSL or TLS, and it will actually give you links to multiple different subdomains that all have different SSL failure conditions on them. So you can actually use this to test out client software, but you can also use it to learn how SSL and TLS looks in Wireshark. So what I'm going to do, the IP of this is a little bit different. So let's actually just do a quick NS lookup to make sure. Okay, 104.154, 85.109. $85.105, 89.105. There we go. Okay, do it on the wireless connection. Now, instead of a NS lookup, I'm going to do a curl. Now, in this case, curl is smart enough to be able to tell you that there is a certificate problem, and it's telling you that it is a self-signed certificate. You may run into this scenario and not actually have an error log that is as descriptive as this, which is again why Wireshark comes into play. So let's look at the PCAP. So we've got Cincinnati ACK, client hello, naked ACK, that's all good. In this case, we actually get to the server hello. So the fact that the server is actually sending back a server hello, you can imply that it accepted what was in the client hello. Namely, the version and the Cipher suites were accepted, as well as whatever extensions are listed here are compatible with that server. So it's good that we actually see the server hello packet come in, because it means that we've gone past that stage and we're going to decide on a few things going forward. So the server hello decided we're doing TLS 1.2. It's decided we're going to choose the Cipher suite here, C02F. And then in that same packet, we've sent the certificate as the next record. So I can actually close down the server hello record and just look at the certificate record. So the certificate is listed here, and right away I can see here the common name is star.badssl.com. Organization is badssl. And then if I'm going to look at the issuer, I can see that the issuer is actually badssl.com themselves, which is the definition of a self-signed cert. So depending on your client configuration, if your client is secure or even public facing or anywhere on the internet, it should not accept self-signed certificates unless explicitly configured to do so. You may see this show up in a browser sometimes when you connect to a website, or even you're running like a local web server and you don't have a certificate attached to it. You may get an error in your browser saying something about a self-signed cert. This is what that is. However, again, if you're troubleshooting something where you don't get a nice error message, you may have to look at this and say, hey, I'm getting the cert, but I'm not getting an intermediate cert with it. I only get one certificate. I'm not getting the root certificate. And when I actually look at the issuer of this, it's actually issued by itself. So you can see that that packet is acknowledged by the client. But in this case, the client is the one that actually sends the SSL alert. And it'll actually send it with a description saying unknown CA. Don't count on this happening. Different implementations of SSL and TLS don't have this description actually included here in plain text for security reasons. So get used to actually looking at the certificate and going through it and trying to pick out different reasons why it would be invalid. The other major reason I find a certificate is invalid is when the validity has expired. So the validity is the window of time in which this certificate is valid. You'll see it listed as a not before time and a not after time. This is really the range of time that this certificate should be considered okay by your client. So 2019, October 9th to 2021, October 8th is the validity period. Looking at the date, we're in that period of time. So at least from the date perspective, the certificate is fine. But we've already identified that it is the fact that it's self-signed that is the problem, and that's why the client's closing it. So in this case, you would have to look at the server side, go into the certificate, figure out, do I have an expired cert? I'm not including the full certificate chain of the intermediate and root, and troubleshoot from the server side to see what you can do to resolve that. But the client's doing what it should. It's not accepting that cert, and it's going to close off the connection. So that's it for TLS troubleshooting with Wireshark. I hope you found this video useful, and if so, please subscribe and like below. This certainly isn't the extent of troubleshooting you can do with Wireshark when it comes to TLS, but I hope this is enough to get you started, at least starting to take some packet captures of TLS connections and start digging through them, either the good cases or some problem cases if you're running into some chronic problems. If you are troubleshooting a network problem and you want to get some advice on it, feel free to post it in the comments, and maybe we can go through it together or even look at the packet capture and analyze it here together on the channel. Take care, everyone, and we'll talk to you next time.